Ford. Summarizing all of mathematics in one book is a daunting and indeed impossible task. Humankind has been exploring and discovering mathematics for millennia.
Humankind has been exploring and discovering mathematics for millennia. Practically, we have relied on math to advance our species.
Humankind has been exploring and discovering mathematics for millennia. Practically, we have relied on math to advance our species, with early arithmetic and geometry providing the foundations for the first cities and civilizations. And philosophically, we have used mathematics as an exercise in pure thought to explore patterns and logic. As a subject, mathematics is surprisingly hard to pin down with one catch-all definition. Mathematics is not simply, as many people think, stuff to do with numbers. That would exclude a huge range of mathematical topics, including much of the geometry and topology covered in this book. Of course, numbers are still very useful tools to understand even the most esoteric areas of mathematics, but the point is that they are not the most interesting aspect of it. Focusing just on numbers misses the forest for the trees. For the record, my own definition of math as the sort of things that mathematicians enjoy doing, while delightfully circular, is largely unhelpful. Big ideas simply explained is actually not a bad definition. Mathematics could be seen as the attempt to find the simplest explanations for the biggest ideas. It is the endeavor of finding and summarizing patterns. Some of those patterns involve the practical triangles required to build pyramids and divide land. Other patterns attempt to classify all of the 26 sporadic groups of abstract algebra. These are very different problems in terms of both usefulness and complexity, but both types of pattern have become the obsession of mathematicians throughout the ages. There is no definitive way to organize all of mathematics, but looking at it chronologically is not a bad way to go. This book uses the historical journey of humans discovering math as a way to classify it and wrangle it into a linear progression, which is a valiant but difficult effort. Our current mathematical body of knowledge has been built up by a haphazard and diverse group of people across time and cultures. So something like the short section on magic squares covers thousands of years and the span of the globe. Magic squares, arrangements of numbers where the sum in each row, column, and diagonal is always the same, are one of the oldest areas of recreational mathematics. Starting in the 9th century BC in China, the story then bounces around via Indian texts from 100 CE, Arab scholars in the Middle Ages, Europe during the Renaissance, and finally modern Sudoku-style puzzles. Across a mere 2 pages, this book has to cover 3,000 years of history, ending with geomagic squares in 2001. And even in this small niche of mathematics, there are many magic square developments that there was simply not enough room to include. The whole book should be viewed as a curated tour of mathematical highlights. Studying even just a sample of mathematics is a great reminder of how much humans have achieved. But it also highlights where mathematics could do better. Things like the glaring omission of women from the history of mathematics cannot be ignored. A lot of talent has been squandered over the centuries, and a lot of credit has not been appropriately given. But I hope that we are now improving the diversity of mathematicians and encouraging all humans to discover and learn about mathematics. Because going forward, the body of mathematics will continue to grow. Had this book been written a century earlier, it would have been much the same up until about page 280. And then it would have ended. No ring theory from Emmy Noether, no computing from Alan Turing, and no 6 degrees of separation from Kevin Bacon. And no doubt that will be true again 100 years from now. The edition printed a century from now will carry on past page 325, covering patterns totally alien to us. And because anyone can do math, there is no telling who will discover this new math, and where or when. To make the biggest advancement in mathematics during the 21st century, we need to include all people. I hope this book helps inspire everyone to get involved. Matt Parker. Introduction. The history of mathematics reaches back to prehistory, when early humans found ways to count and quantify things. In doing so, they began to identify certain patterns and rules in the concepts of numbers, sizes, and shapes. They discovered the basic principles of addition and subtraction, for example, that two things when added to another two invariably resulted in four things. While such ideas may seem obvious to us today, they were profound insights for their time. They also demonstrate that the history of mathematics is above all a story of discovery rather than invention. Although it was human curiosity and intuition that recognized the underlying principles of mathematics, and human ingenuity that later provided various means of recording and notating them, those principles themselves are not a human invention. The fact that 2 plus 2 is equal to 4 is true, independent of human existence. The rules of mathematics, like the laws of physics, are universal, eternal, and unchanging. When mathematicians first showed that the angles of any triangle in a flat plane when added together come to 180 degrees, a straight line, this was not their invention. They had simply discovered a fact that had always been true. Early applications. The process of mathematical discovery began in prehistoric times, with the development of ways of counting things people needed to quantify. At its simplest, this was done by cutting tally marks in a bone or stick, a rudimentary but reliable means of recording numbers of things. In time, words and symbols were assigned to the numbers and the first systems of numerals began to evolve, a means of expressing operations such as acquisition of additional items, or depletion of a stock, the basic operations of arithmetic. As hunter-gatherers turned to trade and farming, and societies became more sophisticated, arithmetical operations and a numeral system became essential tools in all kinds of transactions. To enable trade, stocktaking, and taxes in uncountable goods such as oil, flour, or plots of land, systems of measurement were developed, putting a numerical value on dimensions such as weight and length. Calculations also became more complex, developing the concepts of multiplication and division from addition and subtraction, allowing the area of land to be calculated, for example. In the early civilizations, these new discoveries in mathematics, and specifically the measurement of objects in space, became the foundation of the field of geometry, knowledge that could be used in building and toolmaking. In using these measurements for practical purposes, people found that certain patterns were emerging, which could in turn prove useful. A simple but accurate carpenter's square can be made from a triangle with sides of 3, 4, and 5 units. Without that accurate tool and knowledge, the roads, canals, ziggurats, and pyramids of ancient Mesopotamia and Egypt could not have been built. As new applications for these mathematical discoveries were found, in astronomy, navigation, engineering, bookkeeping, taxation, and so on, further patterns and ideas emerged. The ancient civilizations each established the foundations of mathematics through this interdependent process of application and discovery, but also developed a fascination with mathematics for its own sake, so-called pure mathematics. From the middle of the first millennium BC, the first pure mathematicians began to appear in Greece, and slightly later in India and China, building on the legacy of the practical pioneers of the subject, the engineers, astronomers, and explorers of earlier civilizations. Although these early mathematicians were not so concerned with the practical applications of their discoveries, they did not restrict their studies to mathematics alone. In their exploration of the properties of numbers, shapes, and processes, they discovered universal rules and patterns that raised metaphysical questions about the nature of the cosmos, and even suggested that these patterns had mystical properties. Often mathematics was therefore seen as a complementary discipline to philosophy. Many of the greatest mathematicians through the ages have also been philosophers, and vice versa, and the links between the two subjects have persisted to the present day. It is impossible to be a mathematician without being a poet of the soul. Sofia Kovalovsky, a Russian mathematician. Arithmetic and algebra. So began the history of mathematics as we understand it today, the discoveries, conjectures, and insights of mathematicians that form the bulk of this book. As well as the individual thinkers and their ideas, It is a story of societies and cultures, a continuously developing thread of thought from the ancient civilizations of Mesopotamia and Egypt, through Greece, China, India, and the Islamic Empire to Renaissance Europe and into the modern world. As it evolved, mathematics was also seen to comprise several distinct but interconnected fields of study. The first field to emerge, and in many ways the most fundamental, is the study of numbers and quantities, which we now call arithmetic, from the Greek word arithmos. At its most basic, it is concerned with counting and assigning numerical values to things, but also the operations, such as addition, subtraction, multiplication, and division, that can be applied to numbers. From the simple concept of a system of numbers comes the study of the properties of numbers, and even the study of the very concept itself. Certain numbers, such as the constants pi, e, or the prime and irrational numbers, hold a special fascination and have become the subject of considerable study. Another major field in mathematics is algebra, which is the study of structure, the way that mathematics is organized, and therefore has some relevance in every other field. What marks algebra from arithmetic is the use of symbols, such as letters, to represent variables. In its basic form, algebra is the study of the underlying rules of how those symbols are used in mathematics, in equations, for example. Methods of solving equations, even quite complex quadratic equations, had been discovered as early as the ancient Babylonians, but it was medieval mathematicians of the Islamic Golden Age who pioneered the use of symbols to simplify the process, giving us the word algebra, which is derived from the Arabic al-jabr. More recent developments in algebra have extended the idea of abstraction into the study of algebraic structure, known as abstract algebra. Geometry is knowledge of the eternally existent. Pythagoras, ancient Greek mathematician. Geometry and calculus. A third major field of mathematics, geometry, is concerned with the concept of space, and the relationships of objects in space, the study of the shape, size, and position of figures. It evolved from the very practical business of describing the physical dimensions of things, in engineering and construction projects, measuring and apportioning plots of land, and astronomical observations for navigation and compiling calendars. A particular branch of geometry, trigonometry, proved to be especially useful in these pursuits. Perhaps because of its very concrete nature, for many ancient civilizations, geometry was the cornerstone of mathematics, and provided a means of problem-solving and proof in other fields. This was particularly true of ancient Greece, where geometry and mathematics were virtually synonymous. The legacy of great mathematical philosophers such as Pythagoras, Plato, and Aristotle was consolidated by Euclid, whose principles of mathematics based on a combination of geometry and logic were accepted as the subject's foundation for some 2,000 years. In the 1800s, however, alternatives to classical Euclidean geometry were proposed, opening up new areas of study, including topology, which examines the nature and properties not only of objects in space, but of space itself. Since the classical period, mathematics had been concerned with static situations, or how things are at any given moment. It failed to offer a means of measuring or calculating continuous change. Calculus, developed independently by Gottfried Leibniz and Isaac Newton in the 1600s, provided an answer to this problem. The two branches of calculus, integral and differential, offered a method of analyzing such things as the slope of curves on a graph and the area beneath them as a way of describing and calculating change. The discovery of calculus opened up a field of analysis that later became particularly relevant to, for example, the theories of quantum mechanics and chaos theory in the 1900s. Revisiting logic. The late 19th and early 20th centuries saw the emergence of another field of mathematics, the foundations of mathematics. This revived the link between philosophy and mathematics. Just as Euclid had done in the 3rd century BC, scholars including Gottlob Frege and Bertrand Russell sought to discover the logical foundations on which mathematical principles are based. Their work inspired a re-examination of the nature of mathematics itself, how it works, and what its limits are. This study of basic mathematical concepts is perhaps the most abstract field, a sort of metamathematics, yet an essential adjunct to every other field of modern mathematics. In mathematics, the art of asking questions is more valuable than solving problems. George Cantor, German mathematician. New technology, new ideas. The various fields of mathematics, arithmetic, algebra, geometry, calculus, and foundations, are worthy of study for their own sake, and the popular image of academic mathematics is that of an almost incomprehensible abstraction. But applications for mathematical discoveries have usually been found, and advances in science and technology have driven innovations in mathematical thinking. A prime example is the symbiotic relationship between mathematics and computers. Originally developed as a mechanical means of doing the donkey work of calculation to provide tables for mathematicians, astronomers, and so on, the actual construction of computers required new mathematical thinking. It was mathematicians, as much as engineers, who provided the means of building mechanical, and then electronic computing devices, which in turn could be used as tools in the discovery of new mathematical ideas. No doubt, new applications for mathematical theorems will be found in the future too, and with numerous problems still unsolved, it seems that there is no end to the mathematical discoveries to be made. The story of mathematics is one of exploration of these different fields, and the discovery of new ones. But it is also the story of the explorers, the mathematicians who set out with a definite aim in mind, to find answers to unsolved problems, or to travel into unknown territory in search of new ideas, and those who simply stumbled upon an idea in the course of their mathematical journey, and were inspired to see where it would lead. Sometimes the discovery would come as a game-changing revelation, providing a way into unexplored fields. At other times it was a case of standing on the shoulders of giants, developing the ideas of previous thinkers, or finding practical applications for them. This book presents many of the big ideas in mathematics, from the earliest discoveries to the present day, explaining them in layperson's language, where they came from, who discovered them, and what makes them significant. Some may be familiar, others less so. With an understanding of these ideas, and an insight into the people and societies in which they were discovered, we can gain an appreciation of not only the ubiquity and usefulness of mathematics, but also the elegance and beauty that mathematicians find in the subject. Mathematics, rightly viewed, possesses not only truth, but supreme beauty. Bertrand Russell, British philosopher and mathematician. Introduction. As early as 40,000 years ago, humans were making tally marks on wood and bone as a means of counting. They undoubtedly had a rudimentary sense of number and arithmetic, but the history of mathematics only properly began with the development of numerical systems in early civilizations. The first of these emerged in the 6th millennium BC, in Mesopotamia, Western Asia, home to the world's earliest agriculture and cities. Here, the Sumerians elaborated on the concept of tally marks, using different symbols to denote different quantities, which the Babylonians then developed into a sophisticated numerical system of cuneiform characters. From about 4000 BC, the Babylonians used elementary geometry and algebra to solve practical problems, such as building, engineering, and calculating land divisions, alongside the arithmetical skills they used to conduct commerce and levy taxes. A similar story emerges in the slightly later civilization of the ancient Egyptians. Their trade and taxation required a sophisticated numerical system, and their building and engineering works relied on both a means of measurement and some knowledge of geometry and algebra. The Egyptians were also able to use their mathematical skills in conjunction with observations of the heavens to calculate and predict astronomical and seasonal cycles and construct calendars for the religious and agricultural year. They established the study of the principles of arithmetic and geometry as early as 2000 BC. Greek rigor. The 6th century BC onward saw a rapid rise in the influence of ancient Greece across the eastern Mediterranean. Greek scholars quickly assimilated the mathematical ideas of the Babylonians and Egyptians. The Greeks used a numerical system of base 10 derived from the Egyptians. Geometry in particular chimed with Greek culture, which idolized beauty of form and symmetry. Mathematics became a cornerstone of classical Greek thinking, reflected in its art, architecture, and even philosophy. The almost mystical qualities of geometry and numbers inspired Pythagoras and his followers to establish a cult-like community, dedicated to studying the mathematical principles they believed were the foundations of the universe and everything in it. Centuries before Pythagoras, the Egyptians had used a triangle with sides of 3, 4, and 5 units as a building tool to ensure corners were square. They had come across this idea by observation, and then applied it as a rule of thumb, whereas the Pythagoreans set about rigorously showing the principle, offering a proof that it is true for all right-angled triangles. It is this notion of proof and rigor that is the Greeks' greatest contribution to mathematics. Plato's academy in Athens was dedicated to the study of philosophy and mathematics, and Plato himself described the 5 Platonic solids. Other philosophers, notably Zeno of Elea, applied logic to the foundations of mathematics, exposing the problems of infinity and change. They even explored the strange phenomenon of irrational numbers. Plato's pupil Aristotle, with his methodical analysis of logical forms, identified the difference between inductive reasoning and deductive reasoning. From this basis, Euclid laid out the principles of mathematical proof from axiomatic truths in his Elements, a treatise that was the foundation of mathematics for the next 2 millennia. With similar rigor, Diophantus pioneered the use of symbols to represent unknown numbers in his equations. This was the first step toward the symbolic notation of algebra. A new dawn in the East. Greek dominance was eventually eclipsed by the rise of the Roman Empire. The Romans regarded mathematics as a practical tool rather than worthy of study. At the same time, the ancient civilizations of India and China independently developed their own numerical systems. Chinese mathematics in particular flourished between the 2nd and 5th centuries CE, thanks largely to the work of Liu Hui in revising and expanding the classic texts of Chinese mathematics. In context, key civilization Babylonians field arithmetic before 40,000 years ago. Stone Age people in Europe and Africa count using tally marks on wood or bone. 6,000, 5,000 BC Sumerians develop early calculation systems to measure land and to study the night sky. 4,000, 3,000 BC Babylonians use a small clay cone for 1 and a large cone for 60, along with a clay ball for 10, as their base 60 system evolves. After 2nd century CE, the Chinese use an abacus in their base 10 positional number system. 7th century in India, Brahmagupta establishes 0 as a number in its own right, and not just as a placeholder. It is given to us to calculate, to weigh, to measure, to observe. This is natural philosophy. Voltaire, French philosopher. The first people known to have used an advanced numeration system were the Sumerians of Mesopotamia, an ancient civilization living between the Tigris and Euphrates rivers in what is present-day Iraq. Sumerian clay tablets from as early as the 6th millennium BC include symbols denoting different quantities. The Sumerians, followed by the Babylonians, needed efficient mathematical tools in order to administer their empires. What distinguished the Babylonians from neighbors such as Egypt was their use of a positional number system. In such systems, the value of a number is indicated both by its symbol and its position. Today, for instance, in the decimal system, the position of a digit in a number indicates whether its value is in ones, tens, hundreds, or more. Such systems make calculation more efficient because a small set of symbols can represent a huge range of values. By contrast, the ancient Egyptians used separate symbols for ones, tens, hundreds, thousands, and above, and had no place value system. Representing larger numbers could require 50 or more hieroglyphs. Using different bases. The Hindu, Arabic numeration that is employed today is a base 10 system. It requires only 10 symbols, 9 digits and a 0 as a placeholder. As in the Babylonian system, The position of a digit indicates its value, and the smallest value digit is always to the right. In a base 10 system, a two-digit number, such as 22, indicates 2. 10 plus 2, the value of the 2 on the left is 10 times that of the 2 on the right. Placing digits after the number 22 will create hundreds, thousands, and larger powers of 10. A symbol after a whole number can also separate it from its fractional parts, each representing a tenth of the place value of the preceding figure. The Babylonians worked with a more complex sexagesimal number system that was probably inherited from the earlier Sumerians, and is still used across the world today for measuring time, degrees in a circle, and geographic coordinates. Why they use 60 as a number base is still not known for sure. It may have been chosen because it can be divided by many other numbers, 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. The Babylonians also based their calendar year on the solar year. The number of days in a year was 360 with additional days for festivals. In the Babylonian sexagesimal system, a single symbol was used alone and repeated up to 9 times to represent symbols for 1 to 9. For 10, a different symbol was used, placed to the left of the one symbol, and repeated 2 to 5 times in numbers up to 59. At 60, the original symbol for 1 was reused but placed further to the left than the symbol for 1. Because it was a base 60 system, 2 such symbols signified 61, while 3 such symbols indicated 3661, that is, 60 60 plus 60 plus 1. The base 60 system had obvious drawbacks. It necessarily requires many more symbols than a base 10 system. For centuries, the sexagesimal system also had no place value holders, and nothing to separate whole numbers from fractional parts. By around 300 BC, however, the Babylonians used 2 wedges to indicate no value, much as we use a placeholder 0 today. This was possibly the earliest use of 0. The Babylonian sun god Shamash awards a rod and a coiled rope, ancient measuring devices, to newly trained surveyors, on a clay tablet dating from around 1000 BC. Other counting systems. In Mesoamerica, on the other side of the world, the Mayan civilization developed its own advanced numeration system in the first millennium BC, apparently in complete isolation. Theirs was a base 20 number system, which probably evolved from a simple counting method using fingers and toes. In fact, base 20 number systems were used across the world, in Europe, Africa, and Asia. Language often contains remnants of this system. For example, in French, 80 is expressed as 80. Welsh and Irish also express some numbers as multiples of 20, while in English a score is 20. In the Bible, for instance, Psalm 90 talks of a human lifespan being 80 years and 10, or as great as 80 years. From around 500 BC until the 16th century, when Hindu, Arabic numbers were officially adopted in China, the Chinese used rod numerals to represent numbers. This was the first decimal place value system. By alternating quantities of vertical rods with horizontal rods, this system could indicate ones, tens, hundreds, thousands, and more powers of 10, much as the decimal system does today. For example, 45 was written with 4 horizontal bars, representing 4 10 and 5 vertical bars for 5 1. However, 4 vertical rods followed by 5 vertical rods indicated 405 plus 5 1. The absence of horizontal rods meant there were no tens in the number. Calculations were carried out by manipulating the rods on a counting board. Positive and negative numbers were represented by red and black rods respectively, or different cross-sections. Rod numerals are still used occasionally in China, just as Roman numerals are sometimes used in Western society. The Chinese place value system is reflected in the Chinese abacus. Dating back to at least 200 BC, it is one of the oldest bead counting devices, although the Romans used something similar. The Chinese version, which is still used today, has a central bar and a varying number of vertical wires to separate ones from tens, hundreds, or more. In each column, There are 2 beads above the bar worth 5 each and 5 beads below the bar worth 1 each. The Japanese adopted the Chinese abacus in the 14th century and developed their own abacus, the soroban, which has 1 bead worth 5 above the central bar and 4 beads each worth 1 below the bar in each column. Japan still uses the soroban today. There are even contests in which young people demonstrate their ability to perform soroban calculations mentally, a skill known as onzan. Cuneiform. In the late 1800s, academics deciphered the cuneiform, markings on clay tablets recovered from Babylonian sites in and around Iraq. Such marks, denoting letters and words as well as an advanced number system, were etched in wet clay with either end of a stylus. Like the Egyptians, the Babylonians needed scribes to administer their complex society, and many of the tablets bearing mathematical records are thought to be from training schools for scribes. A great deal has now been discovered about Babylonian mathematics, which extended to multiplication, division, geometry, fractions, square roots, cube roots, equations, and other forms, because, unlike Egyptian papyrus scrolls, the clay tablets have survived well. Several thousand, mostly dating from between 1800 and 1600 BC, are housed in museums around the world. Cuneiform, a word derived from the Latin cuneus, to describe the shape of the symbols, was inscribed into wet clay, stone, or metal. The Babylonian base 60 number system was built from 2 symbols, the single unit symbol, used alone and combined for numbers 1 to 9, and the 10 symbol, repeated for 20, 30, 40, and 50. The Babylonian and Assyrian civilizations have perished. Yet Babylonian mathematics is still interesting, and the Babylonian scale of 60 is still used in astronomy. G. H. Hardy, British mathematician. Modern numeration. The Hindu, Arabic decimal system used throughout the world today has its origins in India. In the 1st to 4th centuries CE, the use of 9 symbols along with 0 was developed to allow any number to be written efficiently, through the use of place value. The system was adopted and refined by Arab mathematicians in the 9th century. They introduced the decimal point, so that the system could also express fractions of whole numbers. 3 centuries later, Leonardo of Pisa popularized the use of Hindu, Arabic numerals in Europe through his book Liber Abaci. Yet the debate about whether to use the new system rather than Roman numerals and traditional counting methods lasted for several hundred years, before its adoption paved the way for modern mathematical advances. With the advent of electronic computers, other number bases became important, particularly binary, a number system with base 2. Unlike the base 10 system with its 10 symbols, binary has just 2, 1 and 0. It is a positional system, but instead of multiplying by 10, each column is multiplied by 2, also expressed as 2, 2, 2 and upward. In binary, the number 111 means 1 2 plus 1 2 plus 1 2. That is 4 plus 2 plus 1, or 7 in our decimal number system. In binary, as in all modern number systems whatever their base, the principles of place value are always the same. Place value, the Babylonian legacy, remains a powerful, easily understood, and efficient way to represent large numbers. The fact that we work in tens as opposed to any other number is purely a consequence of our anatomy. We use our 10 fingers to count. Marcus du Sautoy, British mathematician. Ebisu, the Japanese god of fishermen and one of the 7 gods of fortune, uses a soroban to calculate his profits in the Red Snapper's Dream by Utagawa Tohiro. Mayan numeral system. The Mayans, who lived in Central America from around 2000 BC, used a base 20 number system from around 1000 BC to perform astronomical and calendar calculations. Like the Babylonians, they used a calendar of 360 days plus festivals, to make 365.24 days based on the solar year. Their calendars helped them work out the growing cycles of crops. The Mayan system employed symbols, a dot representing 1 and a bar representing 5. By using combinations of dots over bars, they could generate numerals up to 19. Numbers larger than 19 were written vertically, with the lowest numbers at the bottom, and there is evidence of Mayan calculations up to hundreds of millions. An inscription from 36 BC shows that they used a shell-shaped symbol to denote 0, which was widely used by the 4th century. The Mayans' number system was in use in Central America until the Spanish conquests in the 16th century. Its influence, however, never spread further. See also, the Rhine papyrus, the abacus, negative numbers 0, the Fibonacci sequence, decimals. The Dresden Codex, the oldest surviving Mayan book, dating from the 13th or 14th century, illustrates Mayan number symbols and glyphs. In context: key civilizations. Egyptians, Babylonians, field algebra before. Circa 2000 BC, the Berlin Papyrus records a quadratic equation solved in ancient Egypt. After 7th century CE, the Indian mathematician Brahmagupta solves quadratic equations using only positive integers. 10th century CE, Egyptian scholar Abu Kamil Shuja ibn Aslam uses negative and irrational numbers to solve quadratic equations. 1545, Italian mathematician Girolamo Cardano publishes his Ars Magna, setting out the rules of algebra. Quadratic equations are those involving unknown numbers to the power of 2 but not to a higher power. They contain x but not x, and so on. One of the main rudiments of mathematics is the ability to use equations to work out solutions to real-world problems. Where those problems involve areas or paths of curves such as parabolas, quadratic equations become very useful, and describe physical phenomena, such as the flight of a ball or a rocket. Ancient roots. The history of quadratic equations extends across the world. It is likely that these equations first arose from the need to subdivide land for inheritance purposes, or to solve problems involving addition and multiplication. One of the oldest surviving examples of a quadratic equation comes from the ancient Egyptian text known as the Berlin Papyrus. The problem contains the following information: the area of a square of 100 cubits is equal to that of 2 smaller squares. The side of one of the smaller squares is equal to 1/2 plus 1/4 of the side of the other. In modern notation, this translates into two simultaneous equations: x plus y equals 100 and x equals y equals y. These can be simplified to the quadratic equation plus y equals 100 to find the length of a side on each square. The Egyptians used a method called false position to determine the solution. In this method, the mathematician selects a convenient number that is usually easy to calculate, then works out what the solution to the equation would be using that number. The result shows how to adjust the number to give the correct solution to the equation. For example, in the Berlin Papyrus problem, the simplest length to use for the larger of the two small squares is 4, because the problem deals with quarters. For the side of the smallest square, 3 is used because this length is of the side of the other small square. Two squares created using these false position numbers would have areas of 16 and 9 respectively, which when added together give a total area of 25. This is only of 100, so the areas must be quadrupled to match the Berlin Papyrus equation. The lengths therefore must be doubled from the false positions of 4 and 3 to reach the solutions, 8 and 6. Other early records of quadratic equations are found in Babylonian clay tablets, where the diagonal of a square is given to 5 decimal places. The Babylonian tablet YBC 7289 shows a method of working out the quadratic equation x equals 2 by drawing rectangles and trimming them down into squares. In the 7th century CE, Indian mathematician Brahmagupta wrote a formula for solving quadratic equations that could be applied to equations in the form x plus bx equals c. Mathematicians at the time did not use letters or symbols, so he wrote his solution in words, but it was similar to the modern formula shown above. In the 8th century, Persian mathematician Al-Khwarizmi employed a geometric solution for quadratic equations known as completing the square. Until the 10th century, geometric methods were often used, as quadratic equations were used to solve real-world problems involving land rather than abstract algebraic challenges. The Berlin Papyrus was copied and published by German Egyptologist Hans Schackenberg in 1900. It contains two mathematical problems, one of which is a quadratic equation. Negative solutions. Indian, Persian, and Arab scholars thus far had used only positive numbers. When solving the equation x plus 10x equals 39, they gave the solution as 3. However, this is one of two correct solutions to the problem. Minus 13 is the other. If x is minus 13, x equals 169, and 10x equals minus 130. Adding a negative number gives the same result as subtracting its equivalent positive number. So 169 plus minus 130 is equal to 169. 130 is equal to 39. In the 10th century, Egyptian scholar Abu Kamil Shuja ibn Aslam made use of negative numbers and algebraic irrational numbers as both solutions and coefficients. By the 1500s, most mathematicians accepted negative solutions and were comfortable with surds. They had also started using numbers and symbols, rather than writing equations in words. Mathematicians now utilize the plus or minus symbol, plus or minus, in solving quadratic equations. With the equation x equals 2, the solution is not just x equals, but x equals plus or minus. The plus or minus symbol is included because two negative numbers multiplied together make a positive number. While equals 2, it is also true that equals 2. In 1545, Italian scholar Gerolamo Cardano published his Ars Magna, in which he explored the problem. What pair of numbers have a sum of 10 and product of 40? He found that the problem led to a quadratic equation which, when he completed the square, gave no numbers available to mathematicians at the time gave a negative number when multiplied by themselves. But Cardano suggested suspending belief and working with the square root of negative 15 to find the equations. Two solutions. Numbers such as would later be known as imaginary numbers. The quadratic formula is a way to solve quadratic equations. By modern convention, quadratic equations include a number, a, multiplied by x, a number, b, multiplied by x, and a number, c, on its own. The illustration above shows how the formula uses a, b, and c to find the value of x. Quadratic equations often equal 0, because this makes them easy to work out on a graph. The x solutions are the points where the curve crosses the x-axis. Politics is for the present, but an equation is for eternity. Albert Einstein. Structure of equations. Modern quadratic equations usually look like x plus bx plus c equals 0. The letters a, b, and c represent known numbers, while x represents the unknown number. Equations contain variables, coefficients, constants, and operators. Terms are the parts separated by operators. They can be a number or variable, or a combination of both. The modern quadratic equation has four terms: x, bx, c, and 0. A graph of the quadratic function y equals x plus bx plus c creates a U-shaped curve called a parabola. This graph plots the points of the quadratic function where a equals 1, b equals 3, and c equals 2. This expresses the quadratic equation x plus 3x plus 2 is equal to 0. The solutions for x are where y equals 0 and the curve crosses the x-axis. These are -2 and -1. Parabolas. A function is a group of terms that defines a relationship between variables. The quadratic function is generally written as y equals x plus bx plus c, which, on a graph, produces a curve called a parabola. When real solutions to x plus bx plus c equals 0 exist, they will be the roots, the points where the parabola crosses the x-axis. Not all parabolas cut the x-axis in two places. If the parabola touches the x-axis only once, this means that there are coincident roots. The simplest equation of this form is y equals x. If the parabola does not touch or cross the x-axis, there are no real roots. Parabolas prove useful in the real world because of their reflective properties. Satellite dishes are parabolic for this reason. Signals received by the dish will reflect off the parabola and be directed to one single point, the receiver. Parabolic objects have special reflective properties. With a parabolic mirror, any ray of light parallel to its line of symmetry will reflect off the surface to the same fixed point. Practical applications. Although they were initially used for working out geometric problems, today quadratic equations are important in many aspects of mathematics, science, and technology. Projectile flight, for example, can be modeled with quadratic equations. An object thrown up into the air will fall back down again as a result of gravity. The quadratic function can predict projectile motion, the height of the object over time. Quadratic equations are used to model the relationship between time, speed, and distance, and in calculations with parabolic objects such as lenses. They can also be used to forecast profits and loss in the world of business. Profit is based on total revenue minus production cost. Companies create a quadratic equation known as the profit function with these variables to work out the optimal sale prices to maximize profits. See also, irrational numbers, negative numbers, Diophantine equations, zero algebra. The binomial theorem, cubic equations, imaginary and complex numbers. Quadratic equations are used by military specialists to model the trajectory of projectiles fired by artillery, such as this MIM-104 Patriot surface-to-air missile, commonly used by the U.S. Army. In context. Key civilization. Ancient Egyptians field arithmetic before. Circa 2480 BC stone carvings record flood levels on the River Nile, measured in cubits, about 20 in, and palms, about 3 inches. Circa 1800 BC, the Moscow Papyrus provides solutions to 25 mathematical problems, including the calculation of the surface area of a hemisphere and the volume of a pyramid. After circa 1300 BC, the Berlin Papyrus is produced. It shows that the ancient Egyptians used quadratic equations. 6th century BC, the Greek scientist Thales travels to Egypt and studies its mathematical theories. The Rhine Papyrus in the British Museum in London provides an intriguing account of mathematics in ancient Egypt. Named after Scottish antiquarian Alexander Henry Rhind, who purchased the papyrus in Egypt in 1858, it was copied from earlier documents by a scribe, Amos, more than 3,500 years ago. It measures 12 in by 78 in and includes 84 problems concerned with arithmetic, algebra, geometry, and measurement. The problems, recorded in this and other ancient Egyptian artifacts such as the earlier Moscow Papyrus, illustrated techniques for working out areas, proportions, and volumes. The Eye of Horus, an Egyptian god, was a symbol of power and protection. Parts of it were also used to denote fractions whose denominators were powers of 2. The eyeball, for example, represents, while the eyebrow is representing concepts. The Egyptian number system was the first decimal system. It used strokes for single digits and a different symbol for each power of 10. The symbols were then repeated to create other numbers. A fraction was shown as a number with a dot above it. The Egyptian concept of a fraction was closest to a unit fraction, that is, where n is a whole number. When a fraction was doubled, it had to be rewritten as one unit fraction added to another unit fraction. For example, in modern notation would be plus in Egyptian notation. The 84 problems in the Rhine Papyrus illustrate the mathematical methods in common use in ancient Egypt. Problem 24, for example, asks what quantity, if added to its seventh part, becomes 19. This translates as x plus equals 19. The approach applied to problem 24 is known as false position. This technique, used well into the Middle Ages, is based on trial and improvement, choosing the simplest or false value for a variable and adjusting the value using a scaling factor. In the workings for problem 24, 1/7 is easiest to find for the number 7, so 7 is used first as a false value for the variable. The result of the calculation, 7 plus, is 8, not 19, so a scaling factor is needed. To find how far the guess of 7 is from the required quantity, 19 is divided by 8. This produces a result of 2 which is the scaling factor that should be applied. So 7 is multiplied by 2 plus to give the quantity 16 . Many problems in the papyrus deal with working out shares of commodities or land. Problem 41 asks for the volume of a cylindrical store with a diameter of 9 cubits and a height of 10 cubits. The method finds the area of a square whose side length is of the diameter, then multiplies this by the height. The figure of is used as an approximation for the proportion of the area of a square that would be taken up by a circle if it were drawn within the square. This method is used in problem 50 to find the area of a circle, subtract from the diameter of the circle, and find the area of the square with the resulting side length. Ancient Egyptians used vertical lines to denote the numbers 1 to 9. Powers of 10, particularly those inscribed on stone, were depicted as hieroglyphs, picture symbols. Level of accuracy. Since the ancient Greeks, the area of a circle has been found by multiplying the square of its radius with the number pi, written as pi. The ancient Egyptians had no concept of pi, but the calculations in the Rhind papyrus show that they were close to its value. Their circle area calculation, with the circle diameter as twice the radius, can be expressed as, which, simplified, is 25,681 r, giving an equivalent for pi of 25,681. As a decimal, this is about 0.6% greater than the true value of pi. Instruction books. The Rhind and Moscow papyri are the most complete mathematical documents to survive from the height of the ancient Egyptian civilization. They were painstakingly copied by scribes well versed in arithmetic, geometry, and mensuration and are likely to have been used for training of other scribes. Although they captured probably the most advanced mathematical knowledge of the time, they were not seen as works of scholarship. Instead, they were instruction manuals for use in trade, accounting, construction, and other activities that involved measurement and calculation. Egyptian engineers, for example, used mathematics in the building of pyramids. The Rhind papyrus includes a calculation for the slope of a pyramid using the sect, a measure for the horizontal distance traveled by a slope for each drop of 1 cubit. The steeper the side of a pyramid, the fewer the sects. See also, positional numbers Pythagoras calculating pi algebra decimals. The Rhind papyrus scribe used the hieratic system of writing numerals. This cursive style was more compact and practical than drawing complex hieroglyphs. In context. Key civilization. Ancient Chinese field number theory. Before 9th century BC, the Chinese I Ching lays out trigrams and hexagrams of numbers for use in divination. After 1782, Leonard Euler writes about Latin squares in his Recherches sur un nouvel espèce de carrés magiques. 1979, the first Sudoku-style puzzle is published by Dell Magazines in New York. 2001, British electronics engineer Lee Sallows invents magic squares called geomagic squares, which contain geometric shapes rather than numbers. There are thousands of ways in which to arrange the numbers 1 to 9 in a 3x3 grid. Only 8 of these produce a magic square, where the sum of the numbers in each row, column, and diagonal, the magic total, is the same. The sum of the numbers 1 to 9 is 45, as is the sum of all 3 rows or columns. The magic total, therefore, is of 45, or 15. In fact, there is really just one combination of numbers in a magic square. The other 7 are rotations of this combination. Ancient origins. Magic squares are probably the earliest example of recreational mathematics. Their exact origin is unknown, but the first known reference, in the Chinese legend of Lo Shu, dates from 650 BC. In the legend, a turtle appears to the great King Yu as he faces a devastating flood. The markings on the turtle's back form a magic square, with numbers from 1 to 9 represented by circular dots. Because of this legend, the arrangement of odd and even numbers were believed to have magical properties and was used as a good luck talisman through the ages. As ideas from China spread along trade routes such as the Silk Road, other cultures became interested in magic squares. Magic squares are discussed in Indian texts dating from 100 CE, and Brihatsamhita, a book of divination, includes the first recorded magic square in India, used to measure out quantities of perfume. Arab scholars, who created a vital link between the learning of ancient civilizations and the European Renaissance, introduced magic squares to Europe in the 14th century. An order-form magic square appears beneath the bell in Melancholia by the German artist Albrecht Dürer, and wittily includes the engraving's date of 1514. Different-sized squares. The number of rows and columns in a magic square is called its order. For example, a 3x3 magic square is said to have an order of 3. An order 2 magic square does not exist because it would only work if all the numbers were identical. As the orders increase, so do the quantities of magic squares. Order 4 produces 880 magic squares, with a magic total of 34. There are hundreds of millions of Order 5 magic squares, while the quantity of Order 6 magic squares has not yet been calculated. Magic squares have been an enduring source of fascination for mathematicians. The 15th-century Italian mathematician Luca Pacioli, author of De Viribus Quantitatis, on the power of numbers, collected magic squares. In 18th-century Switzerland, Leonhard Euler also became interested in them, and devised a form that he named Latin squares. The rows and columns in a Latin square contain figures or symbols that appear only once in each row and column. One derivation of the Latin square, Sudoku, has become a popular puzzle. Devised in the US in the 1970s, Sudoku took off in Japan in the 1980s, acquiring its now familiar name, which means single digits. A Sudoku puzzle is a 9x9 Latin square with the added restriction that subdivisions of the square must also contain all 9 numbers. The most magically magical of any magic square ever made by a magician. Benjamin Franklin talking about a magic square that he discovered. Once you have one magic square, you can add the same quantity to every number in the square and still end up with a magic square. Similarly, if you multiply all the numbers by the same quantity, you still have a magic square. See also, irrational numbers, Eratosthenes' sieve, negative numbers, the Fibonacci sequence, the golden ratio, Mersenne primes, Pascal's triangle. In context. Key figure. Pythagoras field. Applied geometry before. Circa 1800 BC, the columns of cuneiform numbers on the Plimpton 322 clay tablet from Babylon include some numbers related to Pythagorean triples. 6th century BC, Greek philosopher Thales of Miletus proposes a non-mythological explanation of the universe, pioneering the idea that nature can be interpreted by reason. After c. 380 BC, in the 10th book of his Republic, Plato espouses Pythagoras' theory of the transmigration of souls. c. 300 BC, Euclid produces a formula to find sets of primitive Pythagorean triples. The 6th century BC Greek philosopher Pythagoras is also antiquity's most famous mathematician. Whether or not he was responsible for all the many achievements attributed to him in math, science, astronomy, music, and medicine, there is no doubt that he founded an exclusive community that lived for the pursuit of mathematics and philosophy, and regarded numbers as the sacred building blocks of the universe. Thales of Miletus, one of the 7 sages of ancient Greece, possibly inspired the younger Pythagoras with his geometrical and scientific ideas. They may have met in Egypt. Angles and symmetry. The Pythagoreans were masters of geometry and knew that the sum of the 3 angles of a triangle is equal to the sum of 2 right angles, a fact which 2 centuries later was described by Euclid as the triangle postulate. Pythagoras's followers were also aware of some of the regular polyhedra, These are the perfectly symmetrical three-dimensional shapes that were later known as the Platonic solids. Pythagoras himself is primarily associated with the formula that describes the relationship between the sides of a right-angled triangle. Widely known as Pythagoras' theorem, it states that A plus B equals C, where C is the longest side of the triangle, and A and B represent the other two, shorter sides that are adjacent to the right angle. For example, a right-angled triangle with two shorter sides of lengths 3 inches and 4 inches will have a hypotenuse of length 5 inches. The length of this hypotenuse is found because 3 plus 4 is equal to 5, 9 plus 16 equals 25. Such sets of whole number solutions to the equation A plus B equals C are known as Pythagorean triples. Multiplying the triple 3, 4, and 5 by 2 produces another Pythagorean triple, 6, 8, and 10. The set 3, 4, 5 is called a primitive Pythagorean triple because its components share no common divisor larger than 1. The set 6, 8, 10 is not primitive as its components share the common divisor 2. There is good evidence that the Babylonians and the Chinese were well aware of the mathematical relationship between sides of a right-angled triangle centuries before Pythagoras' birth. However, Pythagoras is believed to have been the first to prove the truth of the formula that states this relationship, and its validity for all right-angled triangles, which is why the theorem takes his name. Pythagorean triples. The sets of three integers that solve the equation A plus B equals C are known as Pythagorean triples, although their existence was known long before Pythagoras. Around 1800 BC, the Babylonians recorded sets of Pythagorean numbers on the Plimpton 322 clay tablet. These show that triples become more spread out as the number line progresses. The Pythagoreans developed methods for finding sets of triples, and also proved that there are an infinite number of such sets. After many of Pythagoras' schools were destroyed in a 6th century BC political purge, Pythagoreans emigrated to other parts of southern Italy, spreading their knowledge of triples across the ancient world. 2 centuries later, Euclid developed a formula to generate triples: A equals mn, B equals 2 million, C equals m plus n. With certain exceptions, m and n can be any two integers, such as 7 and 4, which produce the triple 33, 56, 65. The formula dramatically sped up the process of finding new Pythagorean triples. The smallest, or most primitive, of the Pythagorean triples is a triangle with side lengths 3, 4, and 5. As this graphic shows, 9 plus 16 equals 25. The graphic above demonstrates why the Pythagorean equation works. Within a large square there are 4 right-angled triangles of equal size. They are arranged so that a tilted square is formed in the middle, by the hypotenuses of the 4 triangles. Journeys of discovery. Pythagoras was well-traveled, and the ideas he absorbed from other countries undoubtedly fueled his mathematical inspiration. Hailing from Samos, which was not far from Miletus in western Anatolia, he may have studied at the school of Thales of Miletus under the philosopher Anaximander. He embarked on his travels at the age of 20, and spent many years away. He is thought to have visited Phoenicia, Persia, Babylon, and Egypt, and may also have reached India. The Egyptians knew that a triangle with sides of 3, 4, and 5 would produce a right angle, so their surveyors used ropes of these lengths to construct perfect right angles for their building projects. Observing this method firsthand may have encouraged Pythagoras to study and prove the underlying mathematical theorem. In Egypt, Pythagoras may also have met Thales of Miletus, a keen geometrician, who calculated the heights of pyramids and applied deductive reasoning to geometry. Reason is immortal, all else is mortal. Pythagoras. A Pythagorean community. After 20 years of traveling, Pythagoras eventually settled in Croton, southern Italy, a city with a large Greek population. There, he established the Pythagorean Brotherhood, a community to whom he could teach both his mathematical and philosophical beliefs. Women were welcome in the Brotherhood, and formed a significant part of its 600 members. When they joined, members were obliged to give all their possessions and wealth to the brotherhood, and also swore to keep its mathematical discoveries secret. Under Pythagoras' leadership, the community gained considerable political influence. As well as his theorem, Pythagoras and his close-knit community made numerous other advances in mathematics, but carefully guarded that knowledge. Among their discoveries were polygonal numbers. These, when represented by dots, can form the shapes of regular polygons. For example, 4 is a polygonal number as 4 dots can form a square, and 10 is a polygonal number as 10 dots can form a triangle with 4 dots at the base, 3 dots on the next row, 2 on the next, and 1 dot at the top of the triangle. 2 millennia after Pythagoras, in 1638, Pierre de Fermat enlarged on this idea when he asserted that any number could be written as the sum of up to k gonal numbers. In other words, every single number is the sum of up to 3 triangular numbers, up to 4 square numbers, or up to 5 pentagonal numbers, and so on. For example, 19 can be written as the sum of 3 triangular numbers. 1 plus 3 plus 15 is equal to 19. Fermat could not prove this conjecture. It was only in 1813 that French mathematician Augustin Louis Cauchy completed the proof. Strength of mind rests in sobriety, for this keeps your reason unclouded by passion. Pythagoras. Fascinated by numbers. Another type of number that excited Pythagoras was the perfect number. It was so called because it is the exact sum of all the divisors less than itself. The first perfect number is 6, as its divisors 1, 2, and 3 add up to 6. The second is 28, the third 496, and the fourth 8128. There was no practical value in identifying such numbers, but their quirkiness and the beauty of their patterns fascinated Pythagoras and his brotherhood. By contrast, Pythagoras was said to have an overwhelming fear and disbelief of irrational numbers, numbers that cannot be expressed as fractions of 2 integers, the most famous example being pi. Such numbers had no place among the well-ordered integers and fractions by which Pythagoras claimed the universe was governed. One story suggests that his fear of irrational numbers drove his followers to drown a fellow Pythagorean, Hippasus, for revealing their existence when attempting to find. Pythagoras's reputation for ruthlessness is also highlighted in a story about a member of the Brotherhood who was executed for publicly disclosing that the Pythagoreans had discovered a new regular polyhedron. The new shape was formed from 12 regular pentagons, and known as the dodecahedron, one of the 5 Platonic solids. Pythagoreans revered the pentagon, and their symbol was the pentagram, a 5-pointed star with a pentagon at its center. Breaking the Brotherhood's rule of secrecy by revealing their knowledge of the dodecahedron would therefore have been an especially heinous crime, punishable by death. The finest type of man gives himself up to discovering the meaning and purpose of life itself. This is the man I call a philosopher. Pythagoras. In the School of Athens, painted by Raphael in 1509, 11 for the Vatican in Rome, Pythagoras is shown with a book, surrounded by scholars eager to learn from him. I have often admired the mystical way of Pythagoras, and the secret magic of numbers. Sir Thomas Browne, English polymath. An integrated philosophy. In ancient Greece, mathematics and philosophy were considered complementary subjects, and were studied together. Pythagoras is credited with coining the term philosopher, from the Greek philos and sophos. For Pythagoras and his successors, the duty of a philosopher was the pursuit of wisdom. Pythagoras's own brand of philosophy integrated spiritual ideas with mathematics, science, and reasoning. Among his beliefs was the idea of metempsychosis, which he may have encountered on his travels in Egypt or elsewhere in the Middle East. This held that souls are immortal and at death transmigrate to occupy a new body. In Athens 2 centuries later, Plato was entranced by the idea and included it in many of his dialogues. Later, Christianity, too, embraced the idea of a division between body and soul, and Pythagoras's ideas would become a core part of Western thought. Importantly for mathematics, Pythagoras also believed that everything in the universe related to numbers and obeyed mathematical rules. Certain numbers were endowed with characteristics and spiritual significance in what amounted to a kind of number worship, and Pythagoras and his followers sought mathematical patterns in everything around them. Numbers in harmony. Music was of great importance to Pythagoras. He is said to have considered it a holy science, rather than something simply to be used for entertainment. It was a unifying element in his concept of harmonia, the joining together of the cosmos and the psyche. This may be why he is credited with discovering the link between mathematical ratios and harmony. It is said that, while walking past a blacksmith's forge, he noticed that different notes were produced when hammers of unequal weight were struck against equal lengths of metal. If the weights of the hammers were in exact and particular proportions, their resulting notes were harmonic. The hammers in the forge had individual weights of 6, 8, 9, and 12 units. Those weighing 6 and 12 units sounded the same notes at different pitches. In today's music terminology, they would be said to be an octave apart. The frequency of the note produced by the hammer of weight 6 was double that of the hammer weighing 12, which corresponds with the ratio of their weights. The hammers of weights 12 and 9 produced a harmonious sound, a perfect fourth, as their weights were in the ratio 4:3. The notes made by the hammers of weights 12 and 8 were also harmonious, a perfect fifth, as their weights were in the ratio 3:2. In contrast, the hammers of weights 9 and 8 were dissonant, as 9:8 is not a simple mathematical ratio. By noticing that harmonious musical notes were connected to numerical ratios, Pythagoras was the first to uncover the relationship between mathematics and music. Pythagoras was reputedly an excellent lyre player. This drawing of ancient Greek musicians illustrates two members of the lyre family, the trigonon and the cithara, creating a musical scale. Although scholars have questioned the story of the forge, Pythagoras is also widely credited with another musical discovery. He is said to have experimented with notes produced by lyre strings of different lengths. He found that while a vibrating string produces a note with frequency F, having the length of the string produces a note an octave higher, with frequency 2F. When Pythagoras used the same ratios that produced harmoniously sounding hammers, and applied them to vibrating strings, he similarly produced notes in harmony with one another. Pythagoras then constructed a musical scale, starting with one note and the note an octave above it, filling in the notes between using perfect fifths. This scale was used until the 1500s, when it was replaced by the even-tempered scale, in which the notes between the two octaves are more evenly spaced. Although the Pythagorean scale worked well for music lying within one octave, it was not suited for more modern music, which was written in different keys and extended across several octaves. While there have been many different types of musical scales in use by different cultures, the long tradition of Western music dates back to the Pythagoreans and their quest to understand the relationship between music and mathematical proportions. The numerology of the Divine Comedy by Dante, pictured here in a fresco from the Duomo in Florence, Italy, reflects the influence of Pythagoras, whom Dante mentions several times in his writings. The legacy of Pythagoras. Pythagoras' status as the most famous mathematician from antiquity is justified by his contributions to geometry, number theory, and music. His ideas were not always original, but the rigor with which he and his followers developed them, using axioms and logic to build a system of mathematics, was a fine legacy for those who succeeded him. There is geometry in the humming of the strings, there is music in the spacing of the spheres. Pythagoras. Pythagoras was born around 570 BC on the Greek island of Samos in the eastern Aegean Sea. His ideas have influenced many of the greatest scholars in history, from Plato to Nicholas Copernicus, Johannes Kepler, and Isaac Newton. Pythagoras is thought to have traveled widely, assimilating ideas from scholars in Egypt and elsewhere in the Middle East before establishing his community of around 600 people in Croton, southern Italy, around 518 BC. This ascetic brotherhood required its members to live for intellectual pursuits, while following strict rules of diet and clothing. It is from this time onward that his theorem and other discoveries were probably set down, although no records remain. At the age of 60, Pythagoras is said to have married a young member of the community, Theano, and perhaps had 2 or 3 children. Political upheaval in Croton led to a revolt against the Pythagoreans. Pythagoras may have been killed when his school was set on fire, or shortly afterward. He is said to have died around 495 BC. See also, irrational numbers, the Platonic solids, syllogistic logic, calculating pi, trigonometry, the golden ratio, projective geometry. In context. Key figure. Hippasus field. Number systems before 19th century BC cuneiform inscriptions show that the Babylonians constructed right-angled triangles and understood their properties. 6th century BC in Greece, the relationship between the side lengths of a right-angled triangle is discovered, and is later attributed to Pythagoras. After 400 BC, Theodorus of Cyrene proves the irrationality of the square roots of the non-square numbers between 3 and 17. 4th century BC, the Greek mathematician Eudoxus of Cnidus establishes a strong mathematical foundation for irrational numbers. Any number that can be expressed as a ratio of 2 integers, a fraction, a decimal that either ends or repeats in a recurring pattern, or a percentage, is said to be a rational number. All whole numbers are rational as they can be shown as fractions divided by 1. Irrational numbers, however, cannot be expressed as a ratio of 2 numbers. Hippasus, a Greek scholar, is believed to have first identified irrational numbers in the 5th century BC, as he worked on geometrical problems. He was familiar with Pythagoras' theorem, which states that the square of the hypotenuse in a right-angled triangle is equal to the sum of the squares of the other 2 sides. He applied the theorem to a right-angled triangle that has both shorter sides equal to 1. As 1 plus 1 is equal to 2, the length of the hypotenuse is the square root of 2. Hippasus realized, however, that the square root of 2 could not be expressed as the ratio of 2 whole numbers, that is, it could not be written as a fraction, as there is no rational number that can be multiplied by itself to produce precisely 2. This makes the square root of 2 an irrational number, and 2 itself is termed non-square or square-free. The numbers 3, 5, 7, and many others are similarly non-square, and in each case, their square root is irrational. By contrast, numbers such as 4, 9, and 16 are square numbers, with square roots that are also whole numbers and therefore rational. The concept of irrational numbers was not readily accepted, although later Greek and Indian mathematicians explored their properties. In the 9th century, Arab scholars used them in algebra. Hippasus may have encountered irrational numbers while exploring the relationship between the length of the side of a pentagon and one side of a pentagram formed inside it. He found that it was impossible to express it as a ratio between 2 whole numbers. In decimal terms, the positional decimal system of Hindu, Arabic numeration allowed further study of irrational numbers, which can be shown as an infinite series of digits after the decimal point with no recurring pattern. For example, 0.1010010001, with an extra 0 between. Each successive pair of ones, continuing indefinitely, is an irrational number. Pi, which is the ratio of the circumference of a circle to its diameter, is irrational. This was proved in 1761 by Johann Heinrich Lambert. Earlier estimations of pi had been 3 or 22. Between any 2 rational numbers, another rational number can always be found. The average of the 2 numbers will also be rational, as will the average of that number and either of the original numbers. Irrational numbers can also be found between any 2 rational numbers. One method is to change a digit in a recurring sequence. For example, an irrational number can be found between the recurring numbers 0.124124 and 0.125125. By changing 1 to 3 in the second cycle of 124, to give 0.124324, and doing so again at the 5th, then 9th cycle, increasing the gap between the replacement 3's by 1 cycle each time. One of the great challenges of modern number theory has been establishing whether there are more rational or irrational numbers. Set theory strongly indicates that there are many more irrational numbers than rational numbers, even though there are infinite numbers of each. Hippasus. Details of Hippasus's early life are sketchy, but it is thought that he was born in Metapontum, in Magna Graecia, around 500 BC. According to the philosopher Iamblichus, who wrote a biography of Pythagoras, Hippasus was a founder of a Pythagorean sect called the Mathematici, which fervently believed that all numbers were rational. Hippasus is usually credited with discovering irrational numbers, an idea that would have been considered heresy by the sect. According to one story, Hippasus drowned when his fellow Pythagoreans threw him over the side of a boat in disgust. Another story suggests that a fellow Pythagorean discovered irrational numbers, but Hippasus was punished for telling the outside world about them. The year of Hippasus's death is not known, but is likely to have been in the 5th century BC. Key work: 5th century BC Mystic Discourse. See also Positional numbers, quadratic equations, Pythagoras imaginary and complex numbers, Euler's number. In context. Key figure: Zeno of Elea. Field logic. Before early 5th century BC, the Greek philosopher Parmenides founds the Eleatic school of philosophy in Elea, a Greek colony in southern Italy. After 350 BC, Aristotle produces his treatise Physics, in which he draws on the concept of relative motion to refute Zeno's paradoxes. 1914, British philosopher Bertrand Russell, who described Zeno's paradoxes as immeasurably subtle, states that motion is a function of position with respect to time. Zeno of Elea belonged to the Eleatic school of philosophy that flourished in ancient Greece in the 5th century BC. In contrast to the pluralists, who believed that the universe could be divided into its constituent atoms, Eleatics believed in the indivisibility of all things. Zeno wrote 40 paradoxes to show the absurdity of the pluralist view. 4 of these, the dichotomy paradox, Achilles and the tortoise, the arrow paradox, and the stadium paradox, address motion. The dichotomy paradox shows the absurdity of the pluralist view that motion can be divided. A body moving a certain distance, it says, would have to reach the halfway point before it arrived at the end, and in order to reach that halfway mark, it would first have to reach the quarterway mark, and so on ad infinitum. Because the body has to pass through an infinite number of points, it would never reach its goal. In the paradox of Achilles and the tortoise, Achilles, who is 100 times faster than the tortoise, gives the creature a head start of 100 meters in a race. At the sound of the starting signal, Achilles runs 100 meters to reach the tortoise's starting point, while the tortoise runs 1 meter, giving it a 1 meter lead. Undeterred, Achilles runs another meter. However, in the same time, the tortoise runs 1/100th of a meter, so it is still in the lead. This continues, and Achilles never catches up. The stadium paradox concerns 3 columns of people, each containing an equal number of people. One group is at rest, while the other 2 run past each other at the same speed in opposite directions. According to the paradox, a person in one moving group can pass 2 people in the other moving group in a fixed time, but only 1 person in the stationary group. The paradoxical conclusion is that half a given time is equivalent to double that time. Over the centuries, many mathematicians have refuted the paradoxes. The development of calculus allowed mathematicians to deal with infinitesimal quantities without resulting in contradiction. The paradox of Achilles and the tortoise maintains that a fast object, such as Achilles, will never catch up with a slow one, such as a tortoise. Achilles will get closer to the tortoise, but never actually overtake it. Zeno of Elea. Zeno of Elea was born around 495 BC in the Greek city of Elea. At a young age, he was adopted by the philosopher Parmenides, and was said to have been beloved by him. Zeno was inducted into the school of Eleatic thought, founded by Parmenides. At the age of around 40, Zeno traveled to Athens, where he met Socrates. Zeno introduced the Socratic philosophers to Eleatic ideas. Zeno was renowned for his paradoxes, which contributed to the development of mathematical rigor. Aristotle later described him as the inventor of the dialectical method of logical argument. Zeno collected his arguments in a book, but this did not survive. The paradoxes are known from Aristotle's treatise Physics, which lists 9 of them. Although little is known of Zeno's life, the ancient Greek biographer Diogenes claimed he was beaten to death for trying to overthrow the tyrant Nearchus. In a clash with Nearchus, Zeno is reported to have bitten off the man's ear. See also, Pythagoras' syllogistic logic, calculus, transfinite numbers, the logic of mathematics, the infinite monkey theorem. In context. Key figure: Plato, field geometry. Before 6th century BC, Pythagoras identifies the tetrahedron, cube, and dodecahedron. 4th century BC, Theaetetus, an Athenian contemporary of Plato, discusses the octahedron and icosahedron. After c. 300 BC, Euclid's Elements fully describes the 5 regular convex polyhedra. 1596, German astronomer Johannes Kepler proposes a model of the solar system, explaining it geometrically in terms of Platonic solids. 1735, Leonhard Euler devises a formula that links the faces, vertices, and edges of polyhedra. The perfect symmetry of the 5 Platonic solids was probably known to scholars long before the Greek philosopher Plato popularized the forms in his dialogue Timaeus, written in c. 360 BC. Each of the 5 regular convex polyhedra, 3D shapes with flat faces and straight edges, has its own set of identical polygonal faces, the same number of faces meeting at each vertex, as well as equilateral sides, and same-sized angles. Theorizing on the nature of the world, Plato assigned 4 of the shapes to the classical elements. The cube was associated with earth, the icosahedron with water, the octahedron with air, and the tetrahedron with fire. The 12-faced dodecahedron was associated with the heavens and its constellations. Composed of polygons. Only 5 regular polyhedra are possible, each one created either from identical equilateral triangles, squares, or regular pentagons, as Euclid explained in Book 13 of his Elements. To create a Platonic solid, a minimum of 3 identical polygons must meet at a vertex, so the simplest is a tetrahedron, a pyramid made up of 4 equilateral triangles. Octahedra and icosahedra are also formed with equilateral triangles, while cubes are created from squares, and dodecahedra are constructed with regular pentagons. Platonic solids also display duality. The vertices of one polyhedron correspond to the faces of another. For example, a cube, which has 6 faces and 8 vertices, and an octahedron, form a dual pair. A dodecahedron and an icosahedron form another dual pair. Tetrahedra, which have 4 faces and 4 vertices, are said to be self-dual. Shapes in the universe? Like Plato, later scholars sought Platonic solids in nature and the universe. In 1596, Johannes Kepler reasoned that the positions of the 6 planets then known could be explained in terms of the Platonic solids. Kepler later acknowledged he was wrong, but his calculations led him to discover that planets have elliptical orbits. In 1735, Swiss mathematician Leonhard Euler noted a further property of Platonic solids, later shown to be true for all polyhedra. The sum of the vertices minus the number of edges plus the number of faces always equals 2, that is, V plus F equals 2. It is also now known that Platonic solids are indeed found in nature, in certain crystals, viruses, gases, and the clustering of galaxies. Plato. Born around 428 BC to wealthy Athenian parents, Plato was a student of Socrates, who was also a family friend. Socrates' execution in 399 BC deeply affected Plato, and he left Greece to travel. During this period, his discovery of the work of Pythagoras inspired a love of mathematics. Returning to Athens, in 387 BC he founded the Academy, inscribing over its entrance the words, "Let no one ignorant of geometry enter here." Teaching mathematics as a branch of philosophy, Plato emphasized the importance of geometry, believing that its forms, especially the 5 regular convex polyhedra, could explain the properties of the universe. Plato found perfection in mathematical objects, believing they were the key to understanding the differences between the real and the abstract. He died in Athens around 348 BC. Key works: c. 375 BC The Republic, c. 360 BC Philebus, c. 360 BC Timaeus. See also Pythagoras, Euclid's Elements, Conic Sections, Trigonometry, Non-Euclidean Geometries, Topology, the Penrose Style. In context. Key figure: Aristotle. Field logic. Before 6th century BC, Pythagoras and his followers develop a systematic method of proof for geometric theorems. After c. 300 BC, Euclid's Elements describes geometry in terms of logical deduction from axioms. 1677 Gottfried Leibniz suggests a form of symbolic notation for logic, anticipating the development of mathematical logic. 1854 George Boole publishes The Laws of Thought, his second book on algebraic logic. 1884 The Foundations of Arithmetic by German mathematician Gottlob Frege examines the logical principles underpinning mathematics. In the square of opposition, S is a subject such as sugar, and P a predicate such as sweet. A and O are contradictory, as are E and I. A and E are contrary. I and O are subcontrary. Both can be true, but both cannot be false. I is a subaltern of A and O is a subaltern of E. In syllogistic logic, this means that if A is true, I must be true, but that if I is false, A must be false as well. In classical Greece, there was no clear distinction between mathematics and philosophy. The two were considered interdependent. For philosophers, one important principle was the formulation of cogent arguments that followed a logical progression of ideas. The principle was based on Socrates' dialectal method of questioning assumptions to expose inconsistencies and contradictions. Aristotle, however, did not find this model entirely satisfactory, so he set about determining a systematic structure for logical argument. First, he identified the different kinds of proposition that can be used in logical arguments, and how they can be combined to reach a logical conclusion. In prior analytics, he describes the propositions as being of broadly 4 types, in the form of all S are P, no S are P, some S are P, and some S are not P, where S is a subject, such as sugar, and P the predicate, a quality, such as sweet. From just 2 such propositions an argument can be constructed and a conclusion deduced. This is, in essence, the logical form known as the syllogism, 2 premises leading to a conclusion. Aristotle identified the structure of syllogisms that are logically valid, those where the conclusion follows from the premises, and those that are not, where the conclusion does not follow from the premises, providing a method for both constructing and analyzing logical arguments. Seeking a rigorous proof. Implicit in his discussion of valid syllogistic logic is the process of deduction, working from a general rule in the major premise, such as all men are mortal, and a particular case in the minor premise, such as Aristotle is a man, to reach a conclusion that necessarily follows, in this case, Aristotle is mortal. This form of deductive reasoning is the foundation of mathematical proofs. Aristotle notes in Posterior Analytics that, even in a valid syllogistic argument, a conclusion cannot be true unless it is based on premises accepted as true, such as self-evident truths or axioms. With this idea, he established the principle of axiomatic truths as the basis for a logical progression of ideas, the model for mathematical theorems from Euclid onward. Aristotle, the son of a physician at the Macedonian court, Aristotle was born in 384 BC in Stagira, Chalkidiki. At the age of about 17, he left to study at Plato's academy in Athens, where he excelled. Soon after Plato's death, anti-Macedonian prejudice forced him to leave Athens. He continued his academic work in Assos. In 343 BC, Philip II recalled him to Macedonia to head the school at the court. One of his students was Philip's son, later known as Alexander the Great. In 335 BC, Aristotle returned to Athens and founded the Lyceum, a rival institution to the academy. In 323 BC, after Alexander's death, Athens again became fiercely anti-Macedonian, and Aristotle retired to his family estate in Chalcis, on Euboea. He died there in 322 BC. Key works: c. 350 BC Prior Analytics c. 350 BC Posterior Analytics c. 350 BC On Interpretation 335, 323 BC Nicomachean Ethics 335, 323 BC Politics. See also Pythagoras Zeno's Paradoxes of Motion Euclid's Elements Boolean Algebra The Logic of Mathematics. In context: Key figure Euclid Field Geometry before c. 600 BC the Greek philosopher, mathematician, and astronomer Thales of Miletus deduces that the angle inscribed inside a semicircle is a right angle. This becomes proposition 31 of Euclid's Elements. c. 440 BC the Greek mathematician Hippocrates of Chios writes the first systematically organized geometry textbook, Elements. After circa 1820 mathematicians such as Carl Friedrich Gauss, Janos Bolyai, and Nikolai Ivanovich Lobachevsky begin to move toward hyperbolic non-Euclidean geometry. Euclid's Elements has a strong claim for being the most influential mathematical work of all time. It dominated human conceptions of space and number for more than 2,000 years and was the standard geometrical textbook until the start of the 1900s. Euclid lived in Alexandria, Egypt, in around 300 BC, when the city was part of the culturally rich Greek-speaking Hellenistic world that flourished around the Mediterranean Sea. He would have written on papyrus, which is not very durable. All that remains of his work are the copies, translations, and commentaries made by later scholars. There is no royal road to geometry. Euclid. Collection of works. The Elements is a collection of 13 books that range widely in subject matter. Books I to 4 tackle plane geometry, the study of flat surfaces. Book V addresses the idea of ratio and proportion, inspired by the thinking of the Greek mathematician and astronomer Eudoxus of Cnidus. Book 6 contains more advanced plane geometry. Books 7 to 9 are devoted to number theory and discuss the properties and relationships of numbers. The long and difficult Book X deals with incommensurables. Now known as irrational numbers, these numbers cannot be expressed as a ratio of integers. Books 11 to 13 examine three-dimensional solid geometry. Book 13 of the Elements is actually attributed to another author, Athenian mathematician and disciple of Plato, Theaetetus, who died in 369 BC. It covers the 5 regular convex solids, the tetrahedron, cube, octahedron, dodecahedron, and icosahedron, which are often called the Platonic solids, and is the first recorded example of a classification theorem. Euclid is known to have written an account of conic sections, but this work has not survived. Conic sections are figures formed from the intersection of a plane and a cone, and they may be circular, elliptical, or parabolic in shape. Euclid. Details of Euclid's date and place of birth are unknown, and knowledge of his life is scant. It is thought that he studied at the academy in Athens, which had been founded by Plato. In the 5th century CE, the Greek philosopher Proclus wrote in his History of Mathematicians that Euclid taught at Alexandria during the reign of Ptolemy Isoter. Euclid's work covers 2 areas: elementary geometry and general mathematics. In addition to the Elements, he wrote about perspective, conic sections, spherical geometry, mathematical astronomy, number theory, and the importance of mathematical rigor. Several of the works attributed to Euclid have been lost, but at least 5 have survived to the 21st century. It is thought that Euclid died between the mid-4th century and the mid-3 RD century BC. Key works: Elements, Conics, Catoptrics, Phenomena, Optics. World of Proof. The title of Euclid's work has a particular meaning that reflects his mathematical approach. In the 1900s, British mathematician John Fauvel maintained that the meaning of the Greek word for element, schia, changed over time from a constituent of a line, such as an olive tree and a line of trees, to a proposition used to prove another, and eventually evolved to mean a starting point for many other theorems. This is the sense in which Euclid used it. In the 5th century CE, the philosopher Proclus talked of an element as a letter of an alphabet, with combinations of letters creating words in the same way that combinations of axioms, statements that are self-evidently true, create propositions. This opening page of Euclid's Elements shows illuminated Latin text with diagrams and comes from the first printed edition, produced in Venice in 1482. Logical deductions. Euclid was not writing in a vacuum. He built upon foundations laid by a number of influential Greek mathematicians who came before him. Thales of Miletus, Hippocrates, and Plato had all begun to move toward the mathematical mindset that Euclid so brilliantly formalized, the world of proof. It is this that makes Euclid unique. His writings are the earliest surviving example of fully axiomatized mathematics. He identified certain basic facts and progressed from there to statements that were sound logical deductions. Euclid also managed to assemble all the mathematical knowledge of his day and organize it into a mathematical structure where the logical relationships between the various propositions were carefully explained. Euclid faced a Herculean task when he attempted to systematize the mathematics that lay before him. In devising his axiomatic system, he began with 23 definitions for terms such as point, line, surface, circle, and diameter. He then put forward 5 postulates. Any 2 points can be joined with a straight line segment. Any straight line segment can be extended to infinity. Given any straight line segment, a circle can be drawn having the segment as its radius and one endpoint as its center. All right angles are equal to one another, and a postulate about parallel lines. He then went on to add 5 axioms, or common notions. If A equals B and B equals C, then A equals C. If A equals B and C equals D, A plus C equals B plus D. If A equals B and C equals D, then AC equals BD. If A coincides with B, then A and B are equal, and the whole of A is greater than part of A. To prove proposition 1, Euclid drew a line with endpoints labeled A and B. Taking each endpoint as a center, he then drew 2 intersecting circles, so that each had the radius AB. This used his third postulate. Where the circles met, he called that point C, and he could draw 2 more lines AC and BC, calling on his first postulate. The radius of the 2 circles is the same, so AC equals AB and BC equals AB. This means that AC equals BC, which is Euclid's first axiom. It follows that AB equals BC equals CA, meaning that he had drawn an equilateral triangle on AB. In Latin translations of elements, deductions end with the letters QEF. The equilateral triangle construction is a good example of Euclid's method. Each step has to be justified by reference to the definitions, the postulates, and the axioms. Nothing else can be taken as obvious, and intuition is regarded as potentially suspect. Euclid's very first proposition was criticized by later writers. They noted, for instance, that Euclid did not justify or explain the existence of C, the point of intersection of the 2 circles. Although apparent, it is not mentioned in his preliminary assumptions. Postulate 5 talks about a point of intersection, but that is between 2 lines, and not 2 circles. Similarly, one of the definitions describes a triangle as a plane figure bounded by 3 lines, which all lie in that plane. However, it seems that Euclid did not explicitly show that the lines AB, BC, and CA lie in the same plane. Postulate 5 is also known as the parallel postulate, because it can be used to prove properties of parallel lines. It says that if a straight line crossing two straight lines creates interior angles on one side that total less than two right angles, lines A and B will eventually cross on that side, if extended indefinitely. Euclid did not use it until Proposition 29, in which he stated that one condition for a straight line crossing two parallel lines was that the interior angles on the same side were equal to two right angles. The fifth postulate is more elaborate than the other four, and Euclid himself seems to have been wary of it. A vital part of any axiomatic system is to have enough axioms, and postulates in the case of Euclid, to derive every true proposition, but to avoid superfluous axioms that can be derived from others. Some asked whether the parallel postulate could be proved as a proposition using Euclid's common notions, definitions, and the other four postulates. If it could, the fifth was unnecessary. Euclid's contemporaries and later scholars made unsuccessful attempts to construct such a proof. Finally, in the 1800s, the fifth postulate was ruled both necessary for Euclid's geometry and independent of his other four postulates. To construct an equilateral triangle, for Proposition 1, Euclid drew a line and centered a circle on its endpoints, here A and B. By drawing a line from each endpoint to C, where the circles intersect, he created a triangle with sides AB, AC, and BC of equal length. Geometry is knowledge of what always exists. Plato. Beyond Euclidean geometry. The Elements also examines spherical geometry, an area explored by two of Euclid's successors, Theodosius of Bithynia and Menelaus of Alexandria. While Euclid's definition of a point addresses a point on the plane, a point can also be understood as a point on a sphere. This raises the question of how Euclid's five postulates can be applied to the sphere. In spherical geometry, almost all the axioms look different from the postulates set out in Euclid's Elements. The Elements gave rise to what is called Euclidean geometry. Spherical geometry is the first example of a non-Euclidean geometry. The parallel postulate is not true for spherical geometry, where all pairs of lines have points in common, nor for hyperbolic geometry, where they can meet infinite numbers of times. Proposition 1. On a given finite straight line, to construct an equilateral triangle. Proposition 2. To place at a given point a straight line equal to a given straight line. Proposition 3. Given two unequal straight lines, to cut off from the greater a straight line equal to the less. Proposition 4. If two sides of one triangle are equal in length to two sides of another triangle, and if the angles contained by each pair of equal sides are equal, then the base of one triangle will equal the base of the other, the two triangles will be of equal area, and the remaining angles in one triangle will be equal to those in the other triangle. Proposition 5. In an isosceles triangle, the angles at the base are equal to one another, and if the equal straight lines are extended below the base, the angles under the base will also be equal to one another. Proposition 6. If in a triangle two angles are equal to one another, the sides separated from the third side by these angles will also be equal. Proposition 7. Given two straight lines constructed on a straight line and meeting in a point, there cannot be constructed on the same straight line, and on the same side of it, two other straight lines meeting in another point and equal to the former two respectively, namely each to that which starts at the same extremity. Proposition 8. If two sides of one triangle are equal in length to two sides of another triangle, and the base of one triangle is equal to the base of the other, the angles of the two triangles will also be equal. Proposition 9. To bisect a given rectilineal angle. Proposition 10. To bisect a given finite straight line. Proposition 11. To draw a straight line at right angles to a given straight line from a given point on it. Proposition 12. To a given infinite straight line, from a given point which is not on it, to draw a perpendicular straight line. Proposition 13. If a straight line set up on a straight line makes angles, it will make either two right angles or angles equal to two right angles. Proposition 14. If with any straight line, and at a point on it, two straight lines not lying on the same side and meeting at the point make adjacent angles equal to two right angles, the two straight lines will be in a straight line with one another. Proposition 15. If two straight lines cut one another, they make the vertical angles equal to one another. Proposition 16. In any triangle, if one of the sides is extended, the angle between the triangle and the extended side is greater than any of the angles inside the triangle. See also, Pythagoras, the Platonic solids, syllogistic logic, conic sections, the problem of maxima, non-Euclidean geometries. In context. Key civilization, ancient Greeks field. Number systems before. c. 18,000 BC in Central Africa, numbers are recorded on bone as carved marks. Circa 3000 BC South American Indians record numbers by tying knots and string. Circa 2000 BC the Babylonians developed positional numbers. After 1202 Leonardo of Pisa commends the Hindu, Arabic number system in Liber Abaci. 1621 in England, William Oughtred invents the slide rule, which simplifies the use of logarithms. 1972 Hewlett-Packard invents an electronic scientific calculator for personal use. The abacus is a counting device and calculator that has been in use since ancient times. It comes in many forms, but all of them work on the same principles. Values of different sizes are represented by counters, arranged in columns or rows. Early abaci. The word abacus may hint at its origins. It is a Latin word derived from the ancient Greek, abax, which means slab or board, a surface that would have been covered in sand and used as a drawing board. The oldest surviving abacus is the Salamis tablet, a marble slab. Made c. 300 BC that is etched with horizontal lines. Pebbles were placed on these lines to count out values. The bottom line represented 0 to 4, the line above counted 5s, and the lines above that 10s, 50s, and so on. The tablet was discovered on the Greek island of Salamis in 1846. Some scholars believe that the Salamis tablet was actually Babylonian. The Greek abax may have come from the Phoenician or Hebrew word for dust, and may refer to far older counting tables developed in Mesopotamian civilizations, where counters were set out on grids drawn in sand. The Babylonian positional number system, developed circa 2000 BC, may have been inspired by the abacus. The Romans upgraded the Greek counting table into a device that greatly simplified calculations. The horizontal rows of the Greek abacus became vertical columns in the Roman abacus, in which were set small pebbles, or calculi in Latin, from which we get the word calculation. A type of abacus was also in use in the pre-Columbian civilizations of Central America. Based on a 5-digit vigesimal, or base 20, counting system, it used corn kernels threaded on strings to represent numbers. No device has survived, but scholars think that the ancient Olmec people invented it 3,000 years ago. By about 1000 C, the Aztec people knew it as the Nepohualtzintzin, the personal accounts counter, and wore it on the wrist as a bracelet. The sunpan shown here is set to the number 917,470,346. The sunpan is traditionally a 2:5 abacus. Each column has 2 heaven beads, each with a value of 5, and 5 earth beads, each with a value of 1, giving a potential value of 15 units. This allows for calculations involving the Chinese base 16 system, which uses 15 units rather than the 9 used in the decimal system. Numbers can be added together by entering the units of one number, starting from the right, then adjusting the beads as further numbers are entered. For subtraction, the units of the first number are entered, then bead values are adjusted downward in each column as further subtracted numbers are entered. Double base. Around the 2nd century CE, abaci had become a common tool in China. The Chinese abacus, or sunpan, matched the design of the Roman version, but rather than use pebbles set in a metal frame, it employed wooden counters on rods, the template for modern abaci. Whether the Roman or Chinese abaci came first is unclear, but their similarities may be a coincidence, inspired by the way people count using the 5 fingers of one hand. Both abaci have 2 decks, the lower deck counting to 5, and the upper deck counting the 5s. By the 2nd millennium CE, the suanpan and its counting methods were becoming widespread across Asia. In the 1300s, it was exported to Japan, where it was called the soroban. This was slowly refined, and by the 1900s, the soroban was a 1:4 abacus. A female personification of arithmetic judges a contest between the Roman mathematician Boethius, who uses numbers, and the Greek Pythagoras, who uses a counting board. The soroban championship. Japanese schoolchildren still use the soroban in mathematics lessons as a way of developing mental arithmetic skills. The soroban is also used for far more complex calculations. Expert soroban users can usually do such calculations more quickly than someone punching the values into an electronic calculator. Every year, the best abacisists from across Japan take part in the soroban championship. They are tested on their speed and accuracy in a knockout system similar to a spelling bee. One of the highlights of the event is Flashanzan trademark, a feat of mental arithmetic in which the players imagine operating an abacus to add 15 three-digit numbers. No physical abacus is allowed. The contestants watch the numbers appear on a big screen, flashing by faster with each round. The 2017 world record for Flashanzan was 15 numbers added together in 1.68 seconds. See also, positional numbers Pythagoras 0 decimals calculus. In context. Key figure. Archimedes' field number theory before. Circa 1650 BC, the Rhind Papyrus, written by Middle Kingdom Egyptian scribes as a mathematics guide, includes estimates of the value of pi. After 5th century CE in China, Zhu Chongji calculates pi to 7 decimal places. 1671 Scottish mathematician James Gregory develops the arctangent method for computing pi. Gottfried Leibniz makes the same discovery in Germany 3 years later. 2019 in Japan, Emma Haruka Ueno uses a cloud computing service to calculate pi to more than 31 trillion decimal places. The fact that pi, the ratio of the circumference of a circle to its diameter, roughly given as 3.141, cannot be expressed exactly as a decimal no matter how many decimal places are calculated has fascinated mathematicians for centuries. Welsh mathematician William Jones was the first to use the Greek letter pi to represent the number in 1706, but its importance for calculating the circumference, an area of a circle, and the volume of a sphere has been understood for millennia. Pi is not merely the ubiquitous factor in high school geometry problems, it is stitched across the whole tapestry of mathematics. Robert Canigel, American science writer. Ancient texts. Determining pi's exact value is not straightforward, and the quest continues to find pi's decimal representation to as many places as possible. 2 of the earliest estimates for pi are given in the ancient Egyptian documents known as the Rhind and Moscow papyri. The Rhind papyrus, thought to have been intended for trainee scribes, describes how to calculate the volumes of cylinders and pyramids and also the area of a circle. The method used to find the area of a circle was to find the area of a square with sides that are of the circle's diameter. Using this method implies that pi is approximately 3.1605 calculated to 4 decimal places, which is just 0.6% greater than the most accurate known value of pi. In ancient Babylon, the area of a circle was found by multiplying the square of the circumference by 12, implying that the value of pi was 3. This value appears in the Bible. And he made the sea of cast bronze, 10 cubits from one brim to the other. It was completely round. Its height was 5 cubits, and a line of 30 cubits measured its circumference. In c. 250 BC, the Greek scholar Archimedes developed an algorithm for determining the value of pi based on constructing regular polygons that exactly fit within, or enclosed, a circle. He calculated upper and lower limits for pi by using Pythagoras's theorem, that the area of the square of the hypotenuse in a right-angled triangle is equal to the sum of the areas of the squares of the other two sides, to establish the relationship between the lengths of the sides of regular polygons when the number of sides w as doubled. This enabled him to extend his algorithm to 96-sided polygons. Determining the area of a circle using a polygon with many sides had been proposed at least 200 years before Archimedes, but he was the first person to consider polygons that were both inscribed and circumscribed.